Welcome to the course on biostatistics and design of experiments. We will talk about something different today, that is called the normality test, because many of these tests assumes that the distribution which you are having is a normal distribution. That means if I take 100 students in my class and measure their heights and then plot it, and mostly it will follow a normal distribution. And you know what is a normal distribution? Mean, median, mode, 3 M's. Mean, median, mode should be equal. Okay, and if I take the average performance of the class and plot it with that of all the students, mostly it should follow a normal distribution. So many of these statistical tests assumes that the distribution which you are having is a normal distribution. So definitely we need to check whether the data which we have is a normal distribution. So that is what is called the normality test. There is something called the skewness, that means the way the distribution has moved to the right or left, and there is also something called the kurtosis, which is an indication of the peakedness of the data. Is it too much peak or it is very flat? Okay, so these are indications of non-normal distribution. Okay, let us look at some points. So when you are testing for normality, the null hypothesis is the data is normally distributed from the normally distributed population, and alternate hypothesis it is a non-normal distribution. So you can from the test accept the null hypothesis or reject the null hypothesis. There are many types of normality tests, many of them. One is called the Anderson-Darling test. Okay. So what it does is it compares the empirical cumulative distribution function of the sample data with the distribution expected the data were normal. If the observed difference is inadequately large, then reject the null hypothesis. Okay. So if you have a data set, from the data set you calculate a mean and a standard deviation, and then you plot that with the data which you have. If it follows normal, mostly the expected and the actual will follow on that line, then we could say it follows a normal distribution. Like this, you will have a max and then on both sides you will have data falling down. Okay, so we can say this data set follows a normal distribution. Whereas you look at this data set, okay, so you have in the lower region large frequency of data, or okay, in upper region you do not have. So when you plot, you calculate this mean and standard deviation and you plot assuming a normal distribution, what is expected and what is observed. So in most of the cases the observed will be much less than what is expected. Okay, that is why these data points are below. Okay, the observed will be what is much less than expected. In fact, this example was taken from this particular reference here actually. So we can say because it does not follow what is expected, the observed is much okay, the expected is much below the observed. Okay, because most of the data is on the left hand side here, as you can see. Obviously this is a non-normal distribution, whereas in this particular case you have maximum data in the center, that is maximum frequency, on either side the frequency goes down. That is a bell shaped curve, that is a uniform distribution. So when you calculate mean and a standard deviation and plot what is expected on one axis and what is observed on another axis, they seem to follow almost on that straight line, whereas in this particular case they do not seem to fall on that straight line. So obviously we reject the null hypothesis, we can say that data is non-normal. Okay. So as I said, this was taken from this particular reference paper, very interesting. Okay. Now in addition to this Anderson-Darling test, there are other tests like Ryan-Joyner test, okay, Kolmogorov-Smirnov test, okay, Shapiro-Wilk test and so on. Okay. So in Ryan-Joyner test, what it does is it calculates a correlation between the sample data and the normal data. Okay. Okay, sample data could be normal or non-normal, okay, and the normal data, and then if the correlation coefficient is very near 1, then we can say this particular data set comes from a normal population. As you know, correlation coefficient is a measure of how closely the data is correlated to the normal data. If it is very less, obviously we can say generally correlation coefficient lies between 0 and 1. If it is very high and closer to 1, we can say that sample data is almost is normal population, otherwise we would say it does not come under the normal population. So, it basically looks at the strength of the correlation coefficient. So, you will reject the null hypothesis for normality if it is the correlation coefficient is large. Now, you have the Kolmogorov, okay, Smirnov normality test. It is an empirical distribution function in which the theoretical cumulative distribution function of the test distribution is contrasted with the ED of the data. So, it calculates an empirical distribution function, okay, for the sample, and there is an empirical distribution function for the normal, and then it compares actually. This Shapiro-Wilk is almost similar to Ryan-Joyner, and basically you are having a correlation between the data and the corresponding normal, okay. So, it is a better test than the this particular, okay. So, we have different approaches by which we could do. So, in the Anderson-Darling test, what we do is from the data set we calculate a mean and a standard deviation, and we predict how the normal curve will look like, and then we compare it, we plot them together with the actual data, and that will give you an observed and expected. If they do not fall on that line, then we can say that the data does not come from the normal population, this as this example shows, which is taken from this particular reference paper. Otherwise, the Ryan-Joyner or the Shapiro-Wilk test, what it does is it calculates a correlation coefficient between the sample data and the normal scores of the data, and then if the correlation coefficient is high, we can say there is a it is very strongly correlated to be a normal distribution, okay. So, another method called Shapiro-Wilk, that also is similar to this Ryan-Joyner method, which is based on a correlation. The another method Kolmogorov, Smirnov, it actually calculates something called empirical distribution function, okay, for the data, as well as it compares with some theoretical EDF, and then tries to predict or try to sum up saying whether the data is a normal population or not actually, okay. So, these are the different tests, and many commercial softwares have all these methods available. So, you just click a button. This is the easiest of these Anderson-Darling, because you can see from the figure very clearly whether the data is falling under the normal or not. So, the observed and the empirical or expected will fall nicely on the straight line. We can tell it is normal, and if the p-value is greater than 0.05, then of course there is no reason for you to reject the null hypothesis, okay. If the data expected and the observed do not fall in this straight line, it falls all over the place, okay, like in this particular example, then obviously it is a not normal, and the p-value will be less than 0.05. So, you reject the null hypothesis and accept the alternate hypothesis, okay. And then the other tests which I mentioned, the Ryan-Joyner test, which calculates something called a correlation coefficient, and then Kolmogorov Smirnov method, which something called empirical distribution function, okay. Then we also have some parameters called skewness and kurtosis. They are also indication of the normality of your data, okay. For example, you can have a negative skew, that means on the negative side you may have less data at the left hand side. Positive skew, that means you have skewed towards the right, this is called a negative skew, this is called a positive skew, okay. So, Excel also has a function called skew. So, given a data set, it calculates what is the skewness of the data. So, I have some data, okay. So I do a skew SKW, skewness is an indication, okay, 0.7065. Okay, so it's plotting something like this, okay. So Excel function is there. For a normal distribution, the skewness factor will be 0, okay. For the normal distribution, the skewness factor will be 0. For an negative skewness means we have skewed to the left, and positive values indicate data that are skewed to the right, okay. So positive value will indicate the data is skewed to the right actually. So this is the formula for skewness. It is called the third moment here. So you have xi, that is data point, each of the data point minus x bar is the average divided by the standard deviation cube actually, and it is calculated for all these data points, okay. So Excel, as I showed you, can calculate your skewness, and it tells you whether it is positively skewed or whether it is negatively skewed, okay. So for example, if I had more of these points, okay, okay. So it is getting pushed, okay, as you can see it becoming bigger and bigger. Okay. So skewness tells you how the shape of the curve is. It is sort of leaning towards the right, that means it is a negative skew. It is leaning towards the left, that means it is a positive skew, okay. And for a normal distribution, the skewness will be 0. Skewness is called the third moment, and we have another term that is called kurtosis. Kurtosis is a measure of peakedness, okay. Suppose you have a normal distribution like this, may have very peaky curve and falling down very fast, or you may have a flat curve, okay. So high kurtosis leads to a very distinct peak near the mean, and it is falling down very rapidly on both sides actually, okay, very heavy tails. Low kurtosis, that means flat. So kurtosis is a fourth moment, as you can see, third moment is skewness, fourth moment is kurtosis, okay. So xi, that means each of the data points minus x bar, that is the mean, divided by standard deviation raised to the power 4. So Excel also has this term called kurtosis, okay. Let us look at the kurtosis also here for your data set, okay. So we can say equal to kurt, okay. So you get some value for kurtosis actually. So if the kurtosis value is very high, you will get a very sharp peak falling on both sides. If it is low kurtosis, the top will be very flat actually. So the skewness and kurtosis determines how the curves look like, okay, and obviously they lead to non-normal distributions, okay. Now this also I taken it from a reference here which is given here. So this is a normal random numbers, normal distribution, okay. So basically you do not see any skewness, that means movement towards left or right, there is no sharp peak, okay. Now look at this particular case, skewness is very small, kurtosis is 2.9, skewness is very small, skewness 0 means it is very normal and well uniformly distributed. In this particular case, as you can see, skewness is 0.06, but kurtosis is very high, 5.9, that is why you get a peak like this, you get a peak like this and both sides it is falling. Now skewness is also high, kurtosis is also high, so you get a distribution like this, okay. Skewness is low, kurtosis is 4.4, okay. Look at this. So you get different types of pictures depending upon the skewness and kurtosis, and each one is called some distribution. This is a normal distribution, this is called a double exponential distribution, Cauchy random distribution, this is Weibull distribution, and so on actually. Okay. And this was taken from this particular reference actually. It is very nice because a normal distribution, bell shaped, there is no leaning towards left or right, whereas when I have very high kurtosis it becomes very peaked. Okay. When you have a larger skewness it is becoming more bent. Okay. As you can see, if the kurtosis is very large, as you can see in this particular example. Okay. So we can have different types of shapes of the distribution depending upon the skewness and kurtosis. Okay. And so we talked about various types of factors which determine the shape of your curve, normal distribution curve, the skewness and kurtosis, and how important it is to determine whether your data set is normal, because in most of the problems we assume normal distribution, most of our calculation we assume normal distribution. So you need to know whether the distribution which you are handling is normal distribution, and the easiest of it is calculate the mean and the standard deviation. Okay. And then we calculate what is expected, and observed is your sample, and see whether they fall in the straight line. If they fall with okay, large p value, then we do not reject the null hypothesis. If they do not fall on that and the p value is much less than 0.05, then we reject the null hypothesis and accept the alternate hypothesis. Okay. So this is what is all about when we are testing for normality. Now there is another statistical calculation that is called odds ratio. It is a point estimation. It is a ratio of two important numbers which gives you some indication of performance of some drugs or the effect of certain treatment and so on, but it is only one point data. Okay. How do you make out sense from just one point data, and that is what this odds ratio is all about actually. Okay. Basically it is a one number summary of data. It is used to infer from the study. It could be like a dose finding trials, maximum tolerable dose. What is the maximum tolerable dose of this particular drug on human? Okay. Or what will be when you are doing a safety study or efficacy trials, what is the median survival? Okay. Okay, what is the response rate? These are all point estimation, and they come under the concept of odds ratio. Okay. Or they also are called hazard ratio also, odds ratio, hazard ratio. Let us look at some examples actually. When you are looking at say change in tumor volume or tumor diameter, that is a continuous variable. Okay. We can calculate mean, we can calculate median for that. If you are looking at how the tumor volume changes in 1 month. Okay. So that is a continuous data. Okay. Binary data, we can have responses, progression, 50% reduction in tumor size. Okay. You all know about this actually, right. Here where we use this odds ratio, whereas if the data is continuous we can use mean, median, mode, range, first quartile, second quartile, fourth quartile, interquartile range, all those things. But when you are having a binary data, then odds ratio come into this picture actually, proportion of male to female having a particular disease, proportion of observed changes in a certain parameter in two different species, and so on actually. In such situations we use this odds ratio. Okay. Okay, let us not go too much into other types of variables. Time to event variables like time of progression, time to death, time to replace. Okay. Then we use median survival, k-year survival hazard ratio. Okay. Then other type of variable is nominal, categorical, ordinal. Let us not go into these things actually. So let us look at an example. Is gender associated with the use of standard adjuvant therapy for patients with newly diagnosed stage 3 colon cancer? Okay. Now 53% of men received this standard adjuvant therapy, 62% of women received standard adjuvant therapy. This was taken from this particular reference actually. Okay, JCO volume 20 March 2002. Okay. So 53% of men received this therapy, 62% of women received this therapy, okay, who were diagnosed with stage 3 colon cancer. Now how do we quantify this difference, because this looks like, can I just take 53, 62 and then I will say 62 minus 53, calling it 9% of men, 9% of more women receive this therapy? That is wrong. This is where odds ratio come into picture. Okay, so odds ratio we can calculate P divided by 1 minus P is for the men 53%. So we will calculate a P divided by 1 minus P is 0.53 divided by 1 minus 0.53, that means 0.47, 0.53 by 0.47 is 1.13. Similarly for female 62%, that is 0.62 divided by 1 minus 0.62. So here 1.62 divided by 0.38 is 1.63. Okay, so we divide this by this, so odd ratio comes out to be 1.44. So a woman is 1.44 times more likely to receive SAT than man. Okay, we do not say that 9% of women, more women received SAT treatment. We need to say a woman is 4.44 times more likely to receive SAT than a man, using this concept of odds ratio as it is called. Okay. So how do you calculate? P divided by 1 minus P, that gives you for the man, P divided by 1 minus P, that gives you for women, and then you take the ratio, that is 1.44. Understand? This odds ratio is very useful in this type of situation, point data. Okay. Let us look at, so the concept is odds ratio OR is P1 divided by 1 minus P1 divided by P2 divided by 1 minus P2. So P1 multiplied by 1 minus P2 divided by P2 multiplied by 1 minus P1. So if OR is greater than 1, increased risk of group 1 when compared to group 2. If OR is equal to 1, there is no difference in risk between group 1 and 2. OR is less than 1, lower risk in group 1 when compared to group 2. See, in this particular example, P1 is the proportion of women who received SAT, P2 is the proportion of men who received SAT. Understand? Okay, so again we can use it in the form of a table. Okay, so SAT, no SAT, women, men. Suppose 298 women received SAT, 250 did not receive, 550 is the total. Men is 202 received SAT, 248 did not receive, that comes to 450. Understand? So how do you calculate odd ratio? P1 298 divided by 1 minus P1 is okay, P1 divided by 1 minus P1 divided by P2 into 1 minus P2. $298 divided by 550 divided by 252 divided by 550 divided by 202 divided by 450, okay, 248 divided by 450. So that comes to 298, okay, multiplied by 252, okay, divided by 202 divided by multiplied by 248. So we get A into D divided by B into C. That is the formula for this odds ratio. Understand? So how do you calculate P1? P1 is nothing but 298 by 550. How do you calculate 1 minus P1? 252 divided by 550. How do you calculate P2? 202 divided by 450. How do you calculate 1 minus P2? 248 divided by 450. Okay, so we have we can cancel all of them. So it comes to 298, okay, divided by 252, 202 divided by 248. So 292 multiplied by 248, 202 multiplied by 252. So 298 is nothing but A, 248 is nothing but D, 252 is nothing but B, 202 is nothing but C. So the odd ratio when you have a table is AD divided by BC. So it comes out to be the same. So P1 divided by 1 minus P1 divided by P2 divided by 1 minus P2 is same as AD divided by BC, very simple. So odds ratio from a 2 by 2 table. So this is an important formula we need to remember, okay. So it ranges from 0 to infinity. In this particular case we got 1.44, so the numbers can be very, very large. It is not symmetric. So when we have 0 to 1 it is protective, greater than 1 it is increased risk. So women are 1.44 times the risk divided by chance of men, men are 0.69 times the risk with respect to chance of women, right, in that particular example of that actually. When we take logarithm of odd ratio, okay, when you take logarithm of 1.44 it comes to 0.36, logarithm for men to men, women to men is 1.44, so the inverse will be men to women, that is 0.69. So when you take it becomes minus 0.36, okay. So when log or odd ratio is greater than 0 it is increased risk, or equal to 0 no difference, or logarithm of or less than 0 is decreased risk, okay. Okay, so just like this, OR greater than 1 increased risk, OR equal to 1 no difference, OR less than 1 lower risk. So when you take a logarithm it becomes 0, greater than 0, equal to 0, less than 0, that is what this table is all about, okay. Okay, okay, when you take the logarithm of that, it's sometimes it is better to take logarithm, especially when you are dealing with very large number of very large data points, okay. So log the or the odds ratio helps us to look at association between two variables. In this particular case we looked at male and female gender, okay, with when you adjust the other variable actually. So in this particular example we are looking at the gender SAT example, okay. So we looked at gender SAT odds ratio is adjusted for of course you have to assume age. When you talk about men and women you should adjust for age, race, they could be coming from different continents, region, northern region, southern region, marital status, whether they are married. So you need to adjust all these things, then only you can do a proper odd ratio, otherwise these values may be confounding your results. So you need to remember that, and it can be used very globally, okay. So that is the beauty of this concept of odd ratio, we can use it as a term if you adjust globally and make it a general statement actually, okay. Now let us look at another example. This is related to paclitaxel, okay. As you know, paclitaxel is a drug which is used for anti-cancer treatment, and there is another type of treatment that is called a CAP treatment, okay, where they give cisplatin. Cisplatin is a platinum based metal anti-cancer drug, okay. So 14 patients, 8 patients were given complete responses, okay. So some patients were given paclitaxel, okay, some patients were given these cisplatin type of drugs, okay. So 14 patients in the CAP group had complete responses, whereas 8 patients in paclitaxel group had complete responses. So P1 is, so if you are doing for CAP 14, we will take P1 as CAP, 14 by 47 is 0.3, P2 is 8 by 47 is 0.17. So odds ratio will be 0.3 by 0.7 divided by 0.17 by 0.83, that comes to be 2.1. So what does that mean? That means 2.1 of the CAP group, okay, and 8 when compared to the paclitaxel group. So we can do the same thing using the table also. So we do 14, total is 47, so we say 14 people complete response, so no response is 33 because 47 is the total, paclitaxel 8 response, no response is 39. So if you want to calculate odd ratio, 14 into this divided by this into this, right. So 14 in the CAP group had response, 8 in paclitaxel group had complete response, okay. So, obviously if you look at the odd ratio 2, how do you name it? Patients in the CAP group are twice as likely to have a complete response as those in the paclitaxel group, okay, and you get the same answer 14 into 39 divided by 33 into 8 actually. 39 divided by 8 into 33, okay, that will give you 2.1. Okay. So, the statement you make is patients in the CAP group are twice as likely to have a complete response when compared to the paclitaxel group. So, we will talk about these things more in the next class, because odds ratio gives you a single point statement for comparing certain data, mostly binary data, live, dead, or a 50% recovery and so on actually. Okay. Thank you very much for your time.